So think of well, what they say is the human nervous system can be compared to a supercomputer with nerve tissue being part of its structure and function. When you look at a computer, all right, and you guys are all in front of a computer right now, whether it's a laptop, a tablet, or your phone, these are all computers. And what does computers do? Computers, they calculate, they make decisions. Decisions based on what they're programmed to do. This is what the computer does. Our nervous system essentially does the same thing. It receives all the input or information that's coming from around outside the world. It processes it, and then it decides what to do. It decides, first of all, it figures out what it means, what value it holds, and then how to respond to it. So this is what the nervous system does. This is the main job of the nervous system, and it's very similar to that of a computer system. Now, what are the different of that nervous system? It includes your brain, of course, and it includes major nerves that come off of the brains, which are called the cranial nerves, right? It includes the spinal cord. And again, depending on who you're speaking to, a lot of people will say that the spinal cord is actually a continuation of the brain. It's the part of the brain that's outside of the cranial vault, right? Spinal cord is the part of the brain outside of the cranial vault. There's also the nerves, the major nerves that come off of the spinal cord, which are called the spinal nerves, right? So the big nerves coming off the brain are called the cranial nerves, and the big ones coming off the spinal cord are called the spinal nerves. There is also what we call to be ganglia. All right, now ganglia is what's ganglia? Ganglia essentially are the cell bodies of ganglia are cell. Would that person close their microphone? Thank you. They're the cell bodies of the neurons outside of the brain and spinal cord. This is what ganglia are. Now, your digestive system, it has its own nervous system. It's independent of the spinal cord and the brain, which you call the enteric plexus. All right. The parts of nerves that are responsible for receiving this information or for gathering that information are referred to as sensory receptors. Now, there's two major divisions for the nervous system, two big parts. There's the central nervous system, or the CNS, and then there's the peripheral nervous system, or the PNS. Okay, CNS and PNS. Now, the central nervous system essentially is just made up of brain and spinal cord. It's brain and spinal cord is the central nervous system. And the peripheral nervous system essentially is just the everything else. Okay, so brain and spinal cord, CNS. Everything else, PNS. CNS, PNS. So again, in this photograph, what they're showing you is you have the brain over here, and then you have the spinal cord over here. Notice that the brain and spinal cord, they're connected. So again, this is why we say that the brain is just a continuation, the spinal cord is a continuation of the brain. It's the part that's processing all that information and carrying it upwards, more central, more cranial, to the brain, I guess, for further processing. So you can see the spinal nerves, and again, these are ganglia. So when you look at these big round parts, that's what they call the ganglia. And again, these are the cell bodies of these neurons, again, of these nerve cells. That's outside cell bodies of the nerve cells outside of the spinal cord and the brain are called ganglia. Okay, so ganglia. Now, the part of the nervous network that controls your digestive organs, it's not connected to spinal cord or brain. This is referred to as the enteric plexus. The enteric plexus, all right? And throughout the body, you have information, you have components of the nervous system that gathers information. These we call sensory receptors. And again, they're showing you over here in this one. that we have these sensory receptors that are located in the skin also. Now, when we move over here, very important to know and understand this part over here. What do we have over here? Central nervous system, right? CNS. And what did you say CNS is? CNS, we said, is brain and spinal cord. Okay? Brain and spinal cord is the CNS. All right. So when you look at this, they end up dividing this into two main parts. A sensory part, in other words, the part that's receiving information, and then there's the other part, the motor part. This is the part that's sending information out to do some type of to bring about some type of a change, to do some type of work. Okay, that's the motor part, right? And then who this motor part connects you to bring about that change is referred to as the effectors, right? So there's somatic nervous system, autonomic nervous system, enteric nervous system, right? This is what we have conscious control over. Okay, we're aware of this, right? So somatic nervous system and special sensory receptors, they call it also. Somatic nervous system, we have control over it, all right? And again, it connects to the brain and spinal cord also. And the brain and spinal cord sends signals out to somatic motor neurons, which eventually connect to muscles, skeletal muscles, all right? So a fly or a bug is walking on your hand, all right? And the somatic receptors, they detect that something is walking on, okay? So that's which part of it? That's going to be the sensory component to it. Over here, you got a bug walking on your arm, all right? The somatic cells, they detect that change. That's part over here, okay? And this is part of what? The peripheral nervous system, PNS. Why? Because again, it's on this is your arms. It's not central is what? Central nervous system, we said, is only brain and spinal cord. Okay, so whatever is not over here, brain and spinal cord, then we're talking about somatic. Okay, so again, there's a fly, there's a bug, there's something walking over here. It gets detected. Now, once it gets detected, that signal then goes to the spinal cord and brain. Then we're at this point over here. That's that part. What happens after that point? After that point, that information, that signal ends up being processed. All right. When that signal gets processed, where is it going to? It goes to another nerve over here, a motor nerve. So there's something walking on your hands, it gets detected by this. All right. When it detects it, it sends it to the brain. It's sent to the spinal cord, and then from the spinal cord, it goes up to the brain. The brain figures out, oh, where is the information coming from, and what does it mean? And what do I do with it? So when the brain figures out, oh, that's a bug, I need to send a signal to the other arm to go and hush, scare that bug away. It sends that signal through these motor neurons. And the motor neurons eventually connects to the muscles that cause your muscles to contract so you can move your arm. Okay? Does that make sense? Question? No questions. Good.
I don't understand. Can you come again? Thank you.
So what do we have over here? You have your brain and spinal cord. Right? Brain and spinal cord. This is your central nervous system. Everything that outside the brain and spinal cord is peripheral nervous system. So CNS and PNS, first thing to understand. That's what we learned at this slide. Central nervous system, brain and spinal cord. Everything else we said is peripheral nervous system. The peripheral, amongst the components that come off of the peripheral nervous system, you have what? Cranial nerves, spinal nerves, and then there's also sensory receptors, right? And there you're going to just give me examples of sensory receptors that you have in your skin. So again, this is going to be part of the peripheral nervous system, right? The sensory receptors you find over here are part of the peripheral nervous system. So imagine you have a bug walking on your hand. There's a bug walking over here. So you have these sensory receptors that are detecting that bug from walking. It's sending information to the spinal cord and brain. That's information that's going in. Okay, that's part of the somatic nervous system. Okay, that's part of the peripheral nervous system. Peripheral nervous system is sending information in. Next, what do we have? Once that information gets to the brain and the brain figures out and understands, yes, there is something moving on this arm, it could be harmful. We need to send a signal to this arm to move it and, scare off that bug or again, brush it off of you. That is part of the peripheral nervous system. Again, that's part of the motor neurons. So when the brain sends a signal down through these motor neurons for these muscles to contract to move the arm, that is done over here by these motor neurons. So again, who did the motor neurons connect to? They connect to the muscles. Muscles contract, then you can move this arm to scare away the bug that's walking here. Okay, that's it. That's all there is. So that's this first part. And this is all under voluntary control. Why? Because you can feel something walking here. You can think about even if nothing's walking here, you know where your hand is. You're able to feel your arm. Okay? You know if your arm is cold or if it's warm. You can move this arm also when you want to, just by thinking. So this is all under voluntary control. It's all under conscious control. Okay? It's voluntary. This is the key thing. Now, moving along. The next part is the autonomic nervous system. All right? You have autonomic sensory receptors and autonomic sensory neurons. So what does the autonomic sensory neurons and receptors do? Pretty much, if we're able to detect something walking on our hands, and we can detect where our arm is and our legs are, and which part of the skin is feeling what, this part we don't have conscious awareness of, and we don't have conscious control of. All right? Who can feel what's inside their stomach right now? Can anybody feel what's inside their stomach? I know you had breakfast. Can you feel you can't feel it. Can you feel what the thyroid gland is doing right now?
No.
All this is under autonomic control. Okay, the sensory receptors are autonomic. You're not consciously aware of what these organs are doing. They're still detecting change, they're still doing their jobs, but you do not have conscious control of that. You're not able to perceive that information. Okay, therefore, you cannot consciously control that either. So it is involuntary. Okay? All that information that your stomach has, it's empty or it's full or it's squeezing out, I don't know, your eggs into your intestine. All that signal goes to the brain. The brain decides what to do with that, and then it sends out signals through motor neurons. And again, those motor neurons from your brains, they're involuntary. You can't control it. And it ends up being divided into two parts, a sympathetic and a parasympathetic. We'll talk about the differences between the two later on. But essentially, they have, very simplistically at this point, what I will say is that they have opposite effects. They do the opposite. If one thing causes something to get more excited, the other one will cause it to get, right? Simple as that. So again, this is under involuntary control. Autonomic nervous system, you do not have conscious control. You can't feel it, and you can't. Who can make their stomach empty right now? Squeeze your stomach. Try and squeeze your stomach. You can't, can you? Make your intestines push the food faster. Can you do that just by thinking about it? No. The answer is you cannot do that. Can you think and make your heart beat faster right now, on demand? Tell your heart to beat slower. Tell your heart to beat faster. You cannot do it. You don't have conscious control over this. Therefore, it is said to be involuntary. And these autonomic neurons control it. It's a good thing that it's autonomic. Why? Because think about it. Most of you forgot to do your homework, or you're late for everything. You're late to show up to class. You're late to submit assignments. So think about if you were late to adjust your heart rate or your stomach. You would be dead. The vast majority of us, nearly every single creature would be dead if this was not done autonomically. Okay? So when you look at the structures that are controlled, or what the effecting organs are, there's smooth muscle, heart muscle, and glands. Smooth muscle, heart muscle, and gland. They're all controlled by the autonomic nervous system. Lastly, we move on to the enteric nervous system. Now, this enteric nervous system essentially is just these enteric sensory receptors and enteric sensory neurons. And what are they part of? What we learned a little in the last chapter. They're part of the enteric plexus. Okay, this is the part of your digestive system's own, very own nervous system. It's not connected to the brain and spinal cord. It is kind of indirectly connected, but it's not affected by it. Let's put it that way. If you look over here, brain and spinal cord both control all these. They have the capacity to do that. However, it doesn't directly get controlled by the enteric nervous system. Yes, brain and spinal cord, it could have an influence. However, it is not needed to function. Okay, just like heart cells, they can get affected by brain and spinal cord. However, heart does not need the brain to survive, to continue to beat. Heart has its own conduction system. It's completely independent of the brain and the spinal cord. Same thing for the digestive system. It's independent of the brain and spinal cord. Okay, it has its own network. And again, it's involuntary, just like the ANS. You can't think and cause your small intestines and large intestines to contract. So what is it doing? The ANS, it controls smooth muscles and glands of your digestive system, as well as, again, endocrine components of your digestive system, right? So this is what it's responsible for. What else do we have? All right. So again, sensory receptors are also referred to as afferent receptors. Okay, sensory receptors, they're taking information away from the body and sending it to your brain. Sensory receptors, they take information away from the body and send it to the brain. Interneurons, when you talk about interneurons, they decide where to send that information to. All right, they decide where to send the information to. That's a job for interneurons. Motor neurons, or efferent neurons, okay, they're taking information away from the interneurons, or away from the brain or spinal cord, and sending it to muscles or other glands. That's a job for efferent neurons. Efferent neurons, they're sending information away from brain and spinal cord. Sensory neurons are sending information away from the body parts. Okay, A for afferent. Afferent means what? Away from the body part. Efferent means exiting brain and spinal cord. Afferent versus efferent. This is the main component, the main difference between the two. So as I told you earlier, as far as the somatic nervous system goes, somatic nervous system consists of both sensory as well as motor components. So both parts it has. It has a sensory part to it as well as a motor part to it. Again, somatic neurons, they take information from the central nervous system and then they deliver that to skeletal muscles, right? That's what they're doing. That's their job. What's next? All right, so autonomic nervous system, it also has a sensory and a motor component to it. But as I told you earlier, we don't have conscious control of it. We're not aware of it. We're not. Oh, this is really annoying. Where are we? We're over here. Okay. So sensory neurons, we talked about this already. So the autonomic motor neurons, they're taking information from your brain and your spinal cord, and it's sending that information to smooth muscles. Perhaps there's smooth muscles around the blood vessels. It could also be heart muscle. In addition to that, it could be various glands throughout your body. Again, with the exception being those glands that we find within the digestive system, because the enteric nervous plexus ends up taking responsibility over those. Now, as I was telling you earlier, the motor part of the autonomic nervous system, it's made up of two branches. There's a sympathetic part and there's also a parasympathetic part. Now, again, if you remember what I said is the main difference between the two is that they have opposite effects. They kind of regulate one another. So what is the difference between sympathetic and parasympathetic? Well, essentially the sympathetic nervous system, it's part of what we call, or what we say to be the fight or flight, okay? Sympathetic division is known as a flight or flight system, or flight or flight division. The parasympathetic neurons, they're what's said to be the rest and digest. Sympathetic neurons, sympathetic and parasympathetic divisions of the autonomic nervous system. The sympathetic division of the autonomic nervous system kicks in during times of stress. And the parasympathetic division of the autonomic nervous system kicks in when you're relaxing. Okay? So, after you have your dinner at nighttime and you're about to sit down and watch your Netflix or whatever you watch, which system is most prominent?
Parasympathetic.
Parasympathetic, very good. When you're outside walking in your city, wherever you are, and a big dog comes to you and starts barking at you, what do? Which system kicks in?
You run. That's sympathetic.
What's going to cause you to run? Which system kicks in?
Sympathetic.
Sympathetic. Okay, so sympathetic, what does it do? If you think about it, your eyes, right? They will start to, the diameter will change of your iris, your pupils change. Next thing you look is your breathing rate changes, right? After that, you feel your heart, it changes. Along with that, you feel your mouth go dry, okay? However, your mouth goes dry, but your palms, they become very sweaty, all right? All this are responses of sympathetic neurons. Your mouth goes dry. What happens in your mouth? Why is your mouth wet? Why does your mouth have to be wet? Who knows this?
Is the gland?
Yeah, why is that gland making saliva?
To aid food, for food to be grinded properly.
For food to get moist, right? Yes,
Yeah,
moist. So that's why you have saliva in your mouth. So If there's no saliva there, think about it. What's going to happen? You cannot enjoy it, right? So, now when that dog comes to you, are you worried about eating your baklava or whatever else, or your simit? No, right? You don't want that. What do you want?
You want to run
Exactly.
for your life.
The brain is going to decrease the amount of sensations going to your mouth. Same thing. Your digestive organs, the blood vessels that are over there, they actually constrict. Okay? Meaning the smooth muscles, a signal gets sent to them and causes them to contract. All the blood vessels around your digestive organs. Less amount of blood goes there. Where do you think the blood flow is going to increase? What's going to dilate? Which muscles will dilate? Or not smooth muscles that are going towards smooth muscles surrounding blood vessels that are being delivered to skeletal muscles will dilate. You're going to end up getting much more blood flow, an increased amount of blood flowing to skeletal muscles than to digestive organs. Okay? It makes sense. When you need to run, what do you need? What do those muscle cells need to function?
They need energy
Energy, right? Where is that energy going to come from?
from the cells,
No.
Energy is going to come from
ATP.
the muscle.
You need what? You need blood, right? You need increased blood flow to bring that energy. And what are we looking for? We're looking for nutrients, primarily glucose. And in addition to that, we also need what? Oxygen. Which is why, again, when you see that dog, or whenever you're under threat, you start to breathe fast as well, right? The reason you're breathing fast, again, is because
Because we need oxygen.
you need oxygen, that's right. Okay, no oxygen, then no energy is produced. So again, this is what's happening over there. All right. All right, let's take a break. Let's take a break. We'll come back in what, about 10 minutes or so? 15 minutes? 15 minutes break? 20 minutes break is fine. Go ahead. 20 minutes, we'll take a break. 10:50, we'll come back.
Okay.
All right, so let's begin. We had our break for 20 minutes. All right, we're starting off with attendance again. Zainab, Abdi Said, Yasin Bari. Zainab, absent.
I'm here, teacher.
Zakia Hassan, absent. Tariq Anwar Al Hadi, Rayan, absent. Shema Sultan, Shanli. Shema, Sumaya Kharman, Sumaya Kharman. Tongul Yilmaz, Tongul.
Huh?
Tongul Yilmaz, absent. Sena, Sine Noor Sir, Sine Noor Sir, absent. Silin Okunak, Silin Okunak,
I'm here.
Silin is here. Sedanur Karakabak, Sedanur Karakabak. Sara Aliya, Sara,
I'm here, yes. I'm here.
Sara Aliya, Sara
I'm
here.
here, yes, doctor.
Okay.
Yes, yes, yes.
Sara Ahmed, Sara Abdul Latif Ahmed, Sara Sheikh Salim.
Yes, I'm here.
Where's Sara Sheikh Salim?
Yes, I'm here.
I don't see you. I don't see you. You're absent.
No, I'm here.
What's your student ID number?
200 509 477.
Talia Kilich. Talia Kilich. Absent. Sara Abdul Salam Ali. Safia Noor Karadash. Safia. Abdul Qadir. Sadra Al Muntaha Abdul Qadir.
Yes, I am here, teacher.
Okay. Rizan Galib.
Yes, teacher, I am here.
Rehan Ozgun. Rehan Ozgun. Absent. Mastawi. Reem Han Hazim Mastawi.
Yes, teacher, I'm here.
Ragid Hakimi. Ragad Hakimi. Hakimi going once. You're absent. Raed Mansoor Saad. Raed Mansoor Saad. Absent. Rabia Noor. Rabia Aras. Rabia Aras. Mama, Syed,
Talk
Mama.
my name.
I don't know who you are. I'm not repeating myself again.
Rayhan.
Mama, Syed. Mama. No, Mama. Mama's absent. Odiase Owen.
Hi.
Odiasi Omorui Owen. Absent. But that person who's walking, shut the microphone.
Umama is here.
Who?
Umama Sayyid.
Oh, Mama, you're absent.
Yes.
You didn't-
No,
yeah.
I'm present.
Okay, well, you should, I waited for you, and I don't know where
Yes,
you.
sir. Sorry, my microphone was not turning on, but I'm here. I'm present.
Next time, answer your name. Sure, was good. Nuran Al Ghali.
Yes, sir, I'm here.
Nasir.
Yes, I am here.
Noor Akila.
Yes, I am here.
Nora Hassan. Nora Al Rashid Hassan. Nora. Nemo. Nemo Rashid Muhammad.
Yes, I'm here.
Mono Omar Noor. Mono
Yes,
Omar.
I'm here.
Mina Chakirolu. Mina Chakirolu.
Yes, I am here.
Marve Kiratli.
Yes.
Marve. Absent.
Teacher.
Melissa Elif Tak. Melissa Elif Tak. Who is this? M. Al Bashir Amar Dawood Al Ani. Muhammad Bashir Amar Dawood. Kauthar Muhammad. Kauthar
Teacher,
Muhammad.
did you hear me?
Huh?
Teacher.
Kauthar Muhammad.
Yes, I am here, teacher.
Okay. Jovita John William. Jovita John William. Jana Abdul Karim Fauzi.
Yes, sir.
Jana Abdul Karim Fauzi is here. Iram Naz Ulkar.
I'm here.
Iram Atash. Iram Atash is gone. Ilhan Usunda. Ilada Birol.
I'm here.
Ishan Akchay. Ishan Akchay. And then there's Hulda Handam Alam.
Present, sir, I'm here.
Okay. Hilal Ata. Hilal. Hibatullah Mahdi Ali.
Yes, sir, I'm here.
Aneen Al Muhammad. Haneen Abazir. Haneen Abazir. Then there's Haneen Ramadan Olu. Ramadan Olu. Hande Noor Quran. Hande Quran. Hamide Kubra Ertürk. Hamide Ertürk. Gamze Nur Kurban.
Yes, teacher, I'm here.
Who's here? Gamze?
Hanin.
I already marked you absent. Wherever you are. If I called you, you didn't answer, you already marked absent. I'm not going back.
Did you hear me?
Gamze Nur Kurban is absent. Fulin Varolu. Fulin
Sir.
Varolu. Fulin, are you here? There's no Fulin. Faiza Nur Yaman.
Doctor, I'm here. Hanin Ramadan.
Fatma Faiza Nur.
Doctor, I'm here, Jan Abdul Karim.
Faiza Nur, you're absent. So don't tell me if I'm here. If I don't call your name, if you don't respond when I call your name, don't come back a minute later and tell me you're here. Because I already marked you absent by then. Faiza Nur Yaman.
Teacher, did you hear me?
Ezgi Tiryaki.
I'm here.
He's here. Ezra Rahal. Ezra
Yes, teacher, I'm here. I am here.
Engin Jan Talak.
Yes, sir.
Engin. Ezra.
Yes.
Ezra, what's your ID number?
20051016
Wrong.
That's my ID.
Ezra Rahal. You're not
Yeah,
Ezra
teacher.
Rahal.
Yeah, teacher. My number 200509 459.
Emre Yavasher.
I'm here, teacher.
Eda Anim Metin. Eda Anim. Dilan Ardaloğlu. Jala
Yes,
Gönül
teacher, I am here.
Raz. Dilan
I'm here.
No, Chava.
Jala's here. Dilan is here. Bushra
Chava is here.
Aktürk. Bushra Aktürk. Absent. Bushra Nur. I'm sorry, not Bushra Nur. Bushra Lutfi. Misalati. Absent. Burhan Altun. Burcu Şoylar.
Yes, I'm here.
Burcu Mulbey.
I'm here, teacher.
Okay. Burcu Şoylar and Burcu Mulbey both are here.
I'm Burcu Mubay.
Okay. Burcu Şoylar.
Yes, I'm here.
Okay. And then how about Burcu Doğan? Burcu Doğan. Beyza Atli. Beyza Erdoğan. Belinay Şide Oscar. Diline Aslan.
Teacher, we can't hear you.
Yes, we can.
Batul Mazlum. Batul Mazlum.
Yes, teacher.
Qatul is
I'm
here.
Yes, I'm here.
Okay. Aisha Sheval Duman. Aisha Sheval Duman. Aya Muhammad Hassan. Aya Muhammad Abdul Rahman Hassan.
Yes, sir. I'm here.
All right. Aseto Cholo. So,
Yes, I'm here, sir.
Elena Selim Arslan. Elena. Agatha Shop. Agatha.
Yes, sir.
Afan Fazil Bashi.
Someone, I can't hear you very well. Inshallah,
Afan
I'm here.
Fazil Bashi. Afaf Abdullah Yakubi.
Sir, there's a lot of noise. We can't hear you.
Abdul Rahman Al Lababidi. Abdul Rahman Al Lababidi.
This teacher, I don't hear my name. Why?
All right, let's move along. Okay.
Please,
So-
teacher.
Teacher, I didn't hear my name.
Me
Uh,
too. My name.
Me too.
I called you.
Teacher, me too.
Me too.
I was here.
Teacher, you didn't say my name.
Like, I was here since 8:30.
Okay,
Is it
so-
possible?
As far as the autonomic nervous system, so moving along with that, we spoke about the sympathetic and parasympathetic divisions. So moving along with that, the next component as for the ANS and the PNS is the enteric nervous system. ENS, again, as I said before, this is the part of the central nervous system that's controlling your digestive system, your digestive organs. All right. So they refer to this. You guys. These cells, they're specialized to convey information. They conduct information from one cell to the next cell. However, one of the problems, or again, I guess you can consider this to be a problem, is that they're non-mitotic cells. They don't have the ability to regenerate. Okay, once these cells are gone, that's it. Right? They cannot be replenished. If they get damaged, they get killed, then that's it. They're not going to end up coming back. So this is the issue for that. Neuroglia, on the other hand, I told you, neuroglia, these are nursing cells, right? These cells, they're far more numerous than the neuroglia, than the neurons are. They greatly outnumber them. They support, they feed, they protect, they repair some of these nerve cells. Neuroglia, these are mitotic cells. They divide throughout your life. Okay, so neurons, they just convey information. Neuroglia, they help take care of these neurons. They feed them, they protect them. They fix them when they get damaged. Some of them, not all of them. Neurons, they have the capacity to become excitable. Okay, so again, nerve cells possess the property of being electrically excitable. Nerve impulses, they travel very fast, okay, at a specific level also. Their strength doesn't diminish. So nerve impulses, they can go very far distances, and the speeds are very fast as well. So anywhere from a half to 130 meters per second. That's very fast. These are very high speeds. So again, if you think about it, when you step on something with your feet that may be sharp or hot, or too cold, you feel it right away. Okay, so again, the reason you feel nearly instantaneously is because of, again, you look at this upper number, 130 meters per second. That's very fast. This is a typical neuron. Okay, so the typical neuron, essentially, it's made up of this main part over here. This is the cell body of that neuron. Okay, this is the cell body of that neuron. This is the nucleus over here, and these parts over here, these branches that come off of the cell body, are called dendrites. Okay, you can see these little bumpy parts. These are called the dendritic spines of the dendrites that you have here. This area over here, the neck of the neuron, this is its neck. This is called the axon hillock. Okay? Axon hillock over here. And you can see that neurons, they have multiple mitochondria that are present. All right. So after that, at the axon hillock, we have this part over here, this long part here. This is called the axon. Okay, axon. This long part here is the axon. This last part are called the axon terminals. These branches that come off are the axon terminals. And then the very tips of them are the synaptic end bulbs. Okay, and we looked at this in the chapter when we covered muscles, the synaptic end bulbs. This is where the transmission of information will take place between a nerve cell, perhaps a muscle cell, a nerve cell, perhaps another nerve cell, or a nerve cell and a gland. Okay, so this is where the synapse will be. Now you see these little bumps over here, okay, or these gaps that you see over here. Each one of these gaps are referred to as being the node of Ranvier. Node of Ranvier. It's a French name, and I know the French say it differently. I don't care about learning French, nor anything about them for that matter. So again, what do we see over here? This essentially is a coating, right? And in these type of cells, again, so this would be an example of a Schwann cell. We'll talk about the difference between oligodendrocytes and Schwann cells. Schwann cells, essentially, they have a myelin sheath, and they also have a neurolemma that they're composed of. Okay, so these are a couple of different parts to it. We all know about the cytoplasm. Aside from the cytoplasm, there's a sheath, a myelin sheath, and a neurolemma. Okay, neurolemma. The neurolemma, this is the wall for this cell. That's the neurolemma. The cytoplasm is just the area inside, and then you have a sheath, a myelin sheath that's there. And this myelin sheath, essentially what it does is it protects this axon terminal, all right? It shields it against other information that's flowing around. So when you have this myelin sheath that's present, okay, when Schwann cells are present, what ends up happening is the nerve signal, as it's traveling, it doesn't have to pass through the entire length of it. It actually will jump through these nodes of Ranvier. Okay, so it jumps over them, and that speeds up the transmission of information. Okay, this jumping that takes place. All right. We had gone over this in the past. and we had visited the events that take place at a neuromuscular junction. So over here, instead of a neuromuscular junction, this is a junction between two nerve cells. Again, the events are the same. You should know what takes place. As a nerve impulse travels down this axon terminal, it comes to the synaptic end bulb. At the synaptic end bulb, there are calcium gated channels. Okay, these are voltage gated channels. As the electrical impulse comes in, it pops open, it depolarizes and opens up these calcium gated channels. Now calcium enters. Okay, as calcium enters, it's going to go and attach itself to the synaptic vesicles. When it attaches to the synaptic vesicles, handful of chemical reactions take place, and it ends up pushing down these vesicles to the synaptic cleft, where these vesicles, they burst open and the neurotransmitter falls out. All right. The neurotransmitter then will go to the other side onto the postsynaptic neuron, and over there it will open up these ligand gated channels. Again, ligand gated channels. And when it opens up these ligand gated channels, then sodium is able to enter. Now this next neuron, this postsynaptic neuron, will also carry about a nerve impulse. Okay, so make sure you understand this. This is very important, and I'm sure you'll see many questions on this for the exam. All right, so on the nerve fibers again, so what are the different parts? We kind of went axon. All right, so we went over this teledendra. So these parts over here, the ones that I went over, this is what I want you to know. So we went over the axoplasm, or actually we talked about the Schwann cell, the cytoplasm, the myelin sheath, and neurolemma. Yeah. What else do we have over here? Yeah, I think that's about. Yeah, that should be all. I don't think you need to know more than that. So we talked about the synapses. Synapse is the sites between one nerve. The synapse essentially is a gap, okay? It's a junction between a nerve cell and another type of cell. And again, that other type of cell could be another nerve, it could be another neuron, it could be a muscle cell, or it could be a gland. Okay, so these are the three, typically you're going to find these three structures there, okay, after a neuron. So the term presynaptic neuron, again, this is the nerve cell. This is the neuron before the synapse occurs, presynaptic. After the synapse, the neuron that's present is referred to as the postsynaptic cell or the postsynaptic neuron. So again, what does it say? Postsynaptic cell could be either a nerve cell or, again, another type of effector. So that effector, it could be what? It could be a muscle, could be a gland for that matter, okay? Again, postsynaptic cells, it carries impulses away from that synapse. So at the chapter 9 or chapter 10, I think maybe it was chapter 9 or 8, we looked at neuromuscular junctions and all the events that take place at a neuromuscular junction. We also spoke about acetylcholine being a neurotransmitter that's found at the neuromuscular junction. All right, so at the synapse, they could be electrical synapses, or again, they could be chemical in nature. So it's either an electrical synapse or a chemical synapse. Now, between the synapse, so again, before that synapse, that nerve cell, that neuron is called the presynaptic neuron. After that synapse, that nerve cell is called the postsynaptic neuron. Now, sometimes we end up having a synapse occurring between an axon of one neuron and the dendrite of another neuron. And that's what we call that axodendritic synapse. Other times we have a synapse occurring between the axon of one neuron and the cell body of another neuron. And we call that an axosomatic synapse. At other times, you have the axon of one neuron and the axon of another neuron that forms a synapse. And we call that axoaxonic synapse. So essentially what ends up happening with anesthetics and neurotoxins is that they block the signal at the synapse. I'm not going to go into detail, but the junction over here, either certain chemicals such as anesthesia, certain types of local anesthetics, even general anesthetics, as well as toxins or poisons. Some of them, what they end up doing is they interfere over here, okay? This is where the interference occurs. Now, if you cannot open these guys up, then a signal can come through. Or if they stay open constantly, they're not allowed to close, the signal is constantly coming in, you end up getting a contraction, right? So this is what ends up happening. Two ways, two things that that could be done by toxins. Some toxins, again, they put you into a contraction state, like botulinum toxin. Other ones, they block the signal where you can't, again, the muscle or the nerve, the nerve, it's not able to communicate a signal anymore. It ends up getting blocked. Moving along. All right. So we use the example of acetylcholine, right? Acetylcholine is the most common one, and acetylcholine, again, you find mostly between nerves and muscles. You're always going to find it between a nerve and a muscle, acetylcholine. Now, aside from acetylcholine, we know that there's about 100 other neurotransmitters, okay? And again, we said acetylcholine was one of them. Another is glutamate, aspartate. Another big one, okay, that helps calm you down is gamma-aminobutyric acid, or GABA. Okay, gamma-aminobutyric acid. Others are, so epinephrine, or norepinephrine, dopamine also. These are neurotransmitters. And as you know, epinephrine, what does it do? It gets you excited. So you guys can kind of see that some of these play a role in the sympathetic, others play a role during parasympathetic stimulation. Okay, endorphins, nitric oxide, these are all depressors. Serotonin, serotonin is one of the neurotransmitters. Again, it's one of the key and crucial brain neurotransmitters. If not enough, then this is one of the causes for depression amongst many people. A lot of people, they end up suffering from depression because they have low levels of serotonin for one reason or another. Serotonin, it is stimulated by sunlight. So there's many people out there who end up getting, what's known as the winter blues. In the wintertime, what happens? The day is very short. In addition to that, depending on which part of the world you're living in, the daylight is there's not, it's cold outside. It's cloudy. It snows. So it's generally speaking, it's darker outside. There's less sunlight, and the intensity of sunlight also decreases. And especially us now, we tend to stay indoors. We stay inside, especially when it's cold. So it's that lack of getting sunlight that ends up decreasing the amount of serotonin, and then which leads to, seasonal blues or winter blues. And that is because serotonin is not being produced. So now they have medications. And among the different medications they have are what's called these selective serotonin reuptake inhibitors, okay, or SSRIs. SSRIs, selective serotonin reuptake inhibitors, essentially what they do is this. They keep these things open here much longer, okay? Selective serotonin reuptake inhibitor. So what does it mean? It inhibits the reuptake of serotonin. What is serotonin? We said that serotonin is a neurotransmitter, right? So if we keep serotonin over here much longer, these guys, they stay open much longer. There's a lot more simulation going on. Signals keep flowing. This is the job for, this is how these SSRIs work, these selective serotonin reuptake inhibitors, all right? Therefore, they increase the effect of serotonin. Now, again, what causes these? The other thing is this. Let me go along with that. Those of you that are in nutrition and also my nursing students. The problem with this, with SSRIs and other drugs, well, let's just talk about SSRIs, selective serotonin reuptake inhibitors, and depression, is that this, look, there's a cause. The cause for somebody being depressed. A lot of times it could be, well, there's multifactorial. There's lots of factors for that. But again, you guys want easy. That's what you're all about, easy. And you just want to pop a pill, put something in your mouth and fix me. All right? So life doesn't work that good. Yes, there's a pill for that, but you're going to pay a heavy price for it. You take these antidepressants, they help, they work, but what they don't do is that they don't address the underlying cause. And as long as that underlying cause goes unaddressed, the depression will continue. And you're going to be, you'll need to stay on the medications to essentially numb your brain into not being affected by whatever that underlying cause is. So with that said, it's important not only to take medications, but to also seek counseling or psychiatric, psychological counseling as well. It's the combination of the two that's going to end up bringing long-term relief, not just temporarily or permanently going on these pills and not seeing anybody. Unfortunately, people are choosing the easier route where they just pop the pills, they don't go see a psychiatrist or psychologist, and again, they don't address the root cause to whatever the problem is. This is what's very problematic. And this is, especially in the United States, the pills are dispensed very easily. It's a huge issue. So what are some of the underlying causes? Well, a lot of times as far as serotonin goes, you can eat natural foods. There are certain foods you can take, nutrition students, you can find out about that. There's certain supplements you can take that actually help increase the raw material that's needed to produce serotonin. So a lot of times it could be diet related. If you're not eating proper diet, that could lead to the decrease of these serotonin. Again, other times it's just as easy as getting sun exposure. Okay. Other times, again, you can take supplements. Maybe due to increased stress or due to life events, you just need some extra ingredients to produce more serotonin. All right, because all these medications, these SRI, they all have side effects, and a lot of these side effects are very nasty. They're very bad. And the other thing is you end up becoming dependent upon it. When you do stop taking it, you end up having withdrawal symptoms from it. So you have to be aware of the effects that these drugs have. Neurons are very diverse. Not only are they diverse in their size, but they're also very diverse in their shape. When you look at the cell bodies, it could range anywhere from 5 nanometers all the way up to 135 millimeters. 5 microns. So the pattern of dendritic branching, it also is going to be different in different parts. Some neurons, they don't have an axon. Others, they may have very short axons. So they could be classified as being multipolar, bipolar, or unipolar. So let's keep in mind with these 2 points and what's said over here. We'll move on to the next slide. So when you look over here, what we have here is what we call a bipolar, okay? When you look at bipolar neuron, look at where the cell body is located. Cell body is located in the middle, okay, between the two, between this pole and this pole. This is the dendrite, and this is the axon part over here. So this would be called bipolar. Unipolar, the cell body is off to the side of the axon, all right, and the hillock. It's off to one side. That's called unipolar. Multipolar, what do we see? Cell body is towards one pole, okay? It's towards one side. It's upstream to the axon. Multipolar. Very easy to look at. You can understand it by that. Now you look over here. Here's a neuron here. Here's a neuron here. They look very different. This is called a Purkinje cell. This is called a pyramidal cell. When you look at the Purkinje cell, what do we see? Very extensive network of dendrites. Compared to the Purkinje cells, not as extensive, is it? Huh? So Purkinje cell versus pyramidal cell. When we talk about neuroglia, again, we're talking about the nursing cells, the supporting cells, or the glial cells. They constitute, again, they're far greater than the number of neurons, several folds greater. And again, they could be, if you're looking at the sheer volume, they could take up about half the volume of your central nervous system. However, the glial cells, they're far smaller than the neurons, much, much smaller. As far as the limitations go, and we spoke about this earlier, glial cells, they're non-excitable cells, okay? They will never propagate impulses. They will never propagate electrochemical impulses. Glial cells, they also have the ability to multiply and divide within the nervous system, whereas neurons, they do not have that ability, okay? They have a very limited ability to repair. Now there's 6 types of glial cells that we have. So again, neuroglia and glia, you can use this term, you can use these interchangeably. So I might just say glial cell, sometimes I'll say glia or neuroglia, they all mean the same thing. Again, they're interchangeable. So the 6 types of neuroglia. Now, 4 of them, they're found only in the central nervous system. Okay, 4 are found only in the central nervous system. Those are astrocytes, oligodendrocytes, microglia, and ependymal cells, right? It's actually the oligodendrocytes you find only in the brain. This is very important about this. We'll come back to this. Schwann cells and satellite cells, you'll find them exclusively in the peripheral nervous system. Okay, Schwann cells. Schwann cells, they have the ability to repair. Okay, they can fix. But again, this is why if you end up cutting your finger or you end up getting some type of trauma somewhere, on your body, you're generally, after, on the skin at least, after you heal, you're able to feel that again, right? For a certain point, it might be numb, maybe for a month, 2 months, 3 months, but then you start to feel again. The reason you start to feel is because these Schwann cells, they start to repair the nerve cells that have been damaged. However, in the central nervous system, there are no Schwann cells there. The job of the Schwann cells, what they do is carried out by these guys here, the oligodendrocytes. Oligodendrocytes are the equivalent of Schwann cells in the central nervous system. However, they don't have the capacity to repair. Okay, so this is a very big point. This is a huge difference between the neuroglia, again, especially between oligodendrocytes as well as the Schwann cell. So when you look over here, it's just a picture and it's showing you what do we have over here. You're looking at neurons over here. Neurons are connected to, this is a microglia. This is a type of a glial cell. Okay, again, the name, glia. Aside from that, there's astrocytes, another type of glial cell. Here's another type of a glial cell here. Here's another one over here, another microglial cell. This is an oligodendrocyte over here. So again, you can see their shapes are different, their sizes are different also. Now astrocytes, okay, a couple of different types of astrocytes. Protoplasmic astrocytes, we find them in gray matter, and fibrous astrocytes, we find them in white matter. Okay, protoplastic astrocytes and fibrous astrocytes. One is found in gray matter, fibrous in white matter. The processes or the arms of these astrocytes, they connect. You can see over here, they connect with the blood vessels. Okay, so you can see this astrocyte. This is a blood vessel over here, and they kind of connect with it, right? So look, the process of one is connecting with this. This one connects with that. That one connects with this. So this neuron, it ends up being fed again the nutrients or whatever it needs from blood by these astrocytes. This is how critical they are, how important they are, right? Blood vessels are not directly connected to neurons, but again, through intermediaries such as this astrocyte that you see over here. Okay, this is an example of a protoplasmic astrocyte. Moving along. So astrocytes, they have a lot of jobs, okay? They do help provide strength. Again, they help maintain the permeability of the endothelial cells. When you're inside your mother's womb, okay, as an embryo, these astrocytes, they start releasing chemicals that end up later on regulating migration of other cells to end up forming the brain, in addition to regulating its growth. They also help regulate the proper pH in order for nerve generation to take place smoothly. They also help, they think that, it plays a role in memory, in forming and maintaining memory. Now, oligodendrocytes, as far as they go, they form the myelin sheath. Okay, myelin sheath is a wrapping around the axon. Okay, so again, it's just fat and protein covering that you find around certain axons. Okay, and again, when axons are surrounded by this myelin sheath, it speeds up the nerve impulse that's traveling through those axons. Again, microglia, they act as the white blood cells, okay, for the nervous system. They act as phagocytes. They also help remove cellular debris, and again, they can eat up damaged nerve tissue or, again, just junk that's present, metabolites. Ependymal cells, they line the ventricles of your brain, okay, in addition to this, the spinal cord. These ependymal cells, they also form of a special fluid called the cerebrospinal fluid. Okay. Okay, so again, two types of glial cells in the peripheral nervous system, right? We have Schwann cells and also, didn't we talk about this? Schwann cell satellite cells. Okay, yeah, the Schwann cells are also called the neurolemma neurolemocytes. Right? These are the Schwann cells, no other name for that. Again, you're going to find them around the axons of the peripheral nervous system. Schwann cells, they also form the myelin sheath. Now remember what I said. Schwann cells, they have the ability to regenerate. This is what makes them different from the oligodendrocytes. Oligodendrocytes, remember, you're going to find them around the central nervous system. Again, your brain and spinal cord. Everywhere else, you're going to find them over here. Okay? So the satellite cells, they surround the cell bodies of the neurons, okay, of the peripheral nervous system. And what do? They regulate the exchange of materials between the neural cell bodies and interstitial fluid. All right. Myelination. All right. Now remember what myelination I told you about a few slides ago. It's the covering that you find around the axons. Okay. It's just a protein lipid covering. And again, we call that covering the myelin sheath. Axons that have this myelin sheath around them, around their axons, let me rephrase that. Neurons that have myelin sheath around their axons are said to be myelinated. Neurons that do not have a myelin sheath around their axons are said to be unmyelinated. Okay, myelinated, unmyelinated. Now, two types of neuroglia, they produce myelin sheath. Okay, and I already told you oligodendrocytes and Schwann cells. Remember, the ones you find in your brain are these guys here, the oligodendrocytes. Everywhere else are the Schwann cells. These do not repair damage. These have a limited ability to repair. So again, you can see over here, what are we looking at? All right, so myelinated and unmyelinated axons. Look at the thick myelin sheath over here. Very thick over here. Compare that to over here. When you look at it, these are not myelinated. Okay. So you have unmyelinated versus myelinated. They just taken and cut, they made a cross section, cut for an axon over here. Again, some more pictures that kind of show the same thing. So gray and white matter, okay? White matter, when you talk about white matter, what is white matter? It's just a collection of myelinated and unmyelinated axons. That's all it is. White matter are just collections of axons that may be myelinated and may be unmyelinated, right? So they're called white matter. Gray matter, on the other hand, it's cell bodies, dendrites, and unmyelinated axons, okay? Axon terminals and neuroglia. So white matter, we're looking at what? Only axons, myelinated and unmyelinated axons. That's it. That's all we're looking at, which is why they end up looking white. When you start looking at all the other components of a neuron, then we say we're looking at, again, in aggregation and collection, then we say gray matter. And again, gray matter, so again, if you have the cell bodies, the dendrites, you have an unmyelinated axon, there's an axon terminal, there's neuroglia, that's all going to be called gray matter. Collectively, that's all called. So these are all areas of gray matter that you see here. And this is all white matter that you see here. What are these white matter? They're just bundles of axons that could be either myelinated or unmyelinated. That's it. That's all they are. Okay, moving along. Neural circuits. So the central nervous system has billions of neurons that are arranged into complex networks. And these networks are referred to as neural circuits, and they all have specific functions as to how they work. So there's simple series circuits, diverging circuits, converging, reverberating, and parallel after discharge circuits. Let's look at them over here. So what do we have over here? Signal comes in through the dendrite, travels on an axon, and then at the now it's going to end up dividing or diverging into 2 more neurons. So, and then each one of these goes off to 2 more. This one will go off to 2 more as well. So again, we call this diverging. It's getting bigger and bigger. Okay? A diverging circuit. Diverging circuit from one neuron. That one neuron ends up connecting to 2 or more postsynaptic neurons. Now, a converging circuit, on the other hand, converging circuit, you have multiple presynaptic neurons that are coming into a single postsynaptic neuron. That's converging. All of these neurons are coming together or converging to a single neuron. When you look at a reverberating circuit, we have a series of neurons, okay, 1 to 4, you have over here. After the impulse is received, it goes down, it travels down, it travels down, and after a certain point, some of that information ends up continuing downwards. Others, it will kind of twist and kind of go in a loop, okay? So some of this information comes down, and now some of that information goes over here, it'll come back and it may go like this again, or it may go up and come down and go around again, okay? Or it may come up like that and again, perhaps go around this way. So this is how it works, okay? And we call this a reverberating circuit. Now, for the last one, this parallel after discharge, the input comes in, and what ends up happening is, again, it diverges, it branches out. Some of it goes to one side, they're parallel to the central neuron. So that's why it's called parallel after discharge. And then they eventually end up converging to a single postsynaptic neuron. Okay. Regeneration, neurogenesis. So, as I mentioned earlier, nerve cells, they have a limited ability to regenerate. Okay, they have a limited ability to regenerate. Some of them they can, others they don't regenerate very well at all. What are some of the factors for that? Well, there's multiple factors for that. At this point, what you should be aware of is what we said before about, where do we go? In terms of regeneration, the presence or absence of Schwann cell or oligodendrocytes. If Schwann cells are present, then we can say that, okay, yeah, it has a limited, it has an ability to regenerate. If there are no Schwann cells, we're looking at oligodendrocytes, then we know that, there's essentially no ability to regenerate. That's the end of it. That's it. When we look at plasticity, again, we're talking about the adaptability of organisms to change in their environments. And that's what it means. So nerve cells, again, they have to be within a very a narrow range of conditions in order to survive. So yes, they do exhibit a certain degree of plasticity. However, from the time you're a child, the number of neurons, the connections that are being made will continue to increase. So again, with that said, the number of cells, they do increase. However, there's a point where that stops. damaged cells, they cannot be regenerated within, in other words, regeneration is, as I already explained to you, it's not possible as much as we know at this point in science. Beyond damage, once they're damaged, that's the end of it. All right, so these are the 2 chapters we covered today. That's all for this week. Next week, we have multiple chapters we're going to be covering. So we have, how many more lectures do we have now? I think we have another 4 weeks left.